Okay, today our topic is software performance modeling. So we will cover a few subtopics, including software performance modeling. What is software performance modeling? And we will talk about the three types of software performance models. The first type is execution graphs or execution models. And we will talk about queuing network models. And finally, we talk about machine learning based performance models. There are lots of references you can check. Okay, there are a few books and the conference papers and also lecture slides from another professor. Okay, so what is software? What are software performance models? So when we talk about the models, we think about some magic, right? Uh, we want to uh, giving some input, we want to generate some output. That is a model, right? For example, for a machine learning model, you have lots of parameters. For example, for uh, for weather prediction for tomorrow, you have lots of parameters from the history from today, right? You have the weather information today, you have weather information from last month, the same day, last year, the same day, right? Then we can predict the weather of tomorrow, right? So that's, we have input, we have output. Output is tomorrow's weather, okay? Uh, Similarly, for software performance models, we have inputs and outputs. So what are the inputs? What are the outputs? So here we talk about. So formally, uh, software performance models are formal representations of the software to capture aspects and information of the performance, right? Uh, it's built as early as design architecture models to express and understand the non-functional requirements. So we can build software performance models during our software testing after we get the software testing results. We can also build performance models very early doing software design and software architecture. From there, these models allow us to understand the performance, to understand whether the architecture can satisfy our performance requirements, to understand how to choose one architecture among several alternatives. Okay. Yeah, the benefits of software performance models. They allow us to estimate the performance of software. They allow us to estimate resource needs, identify performance issues as early as possible, simulate the execution of a software under certain conditions. For example, we have a certain number of users and we have a certain number of CPUs and certain configuration of memories. So we want to simulate this scenario to get what is the CPU usage, what is the response time under such scenario, right? We don't need to actually run this testing or run this scenario to get the performance. We can just use our performance model to simulate it to get the results. Okay. Now we can also establish the software performance for medium, for average, best, and worst case scenarios. So these are the things that software performance models can tell us. Okay. Uh, so software performance models sometimes can provide a graphic representation of the system, right? So it is possible that we derive our performance models from our design models, such as UML models, architecture, sequence diagram, those things. Okay, so unit design models of the system capture the static aspects, but performance models capture the dynamic aspects. Why is this dynamic? Because we want to understand um, during software execution, what is the performance of the software, right? For example, when there are 1,000 users using the system, what is the performance? Okay, so we talk about there are three types of performance models: software execution models, queuing networks, and machine learning based models. So we'll talk about them one by one. Okay, first we discuss what is software execution model. So it is constructed as early I mean, as early as the software design architecture. It's kind of early in the development process to ensure that the chosen software architecture can achieve the required performance requirements. Okay, it provides a static uh, analysis. So here, it's static. Yeah, it's relative static to dynamic. It's you examine the graph and you tell the results of the best, mean, best, and worst case scenarios, right? And so it characterizes the resource requirements of a proposed software alone in the absence of the workloads, multiple users, or delays due to contention for resources. Software execution models is a simple model. It doesn't consider the scenarios when there are multiple users, when there are resource contentions. It just considers there's only one user using the system. What is the result? What is the response time? Okay. So although it is very simple, it is usually sufficient for identify serious performance problems at the architectural and early design phases, right? So at early stage, you build a simple model to identify problems. However, if we don't identify any problems using the software execution model, it doesn't mean there are no problem, right? Later on, when we build a more sophisticated model, we may identify other problems. Okay. Execution graphs. Execution graphs is one type of software execution model. Is a most popular one. It represents the execution of the system in a graph. Okay. So it works well for understanding of the software and its performance, its non-functional requirements. Okay, so what is an execution graph? So let's see. First, these are basic components of one execution graph. The first one is basic nodes, right? It's a box. This one represents processing step at the lowest level of detail, right? For example, for an ATM machine, right? So the basic step, one basic step maybe get card information, right? Get a pin information. So those are basic steps, basic nodes. The second type is expanded nodes, which which represents a combination of basic nodes and other nodes. It represents the processing steps, detailed processing steps are elaborated in another subgraph, right? You can consider it as a function or a sub-process, okay? And there is a repetition nodes, which means the subsequent node is repeated n times, okay? A case node is like in programming, it's like a switch case thing, right? So you can have different branches to go, right? It represents the conditional execution of processing steps, okay? Don't worry, we will look at a simple example to help you understand the notation. A partial node, so which means attaching nodes run in parallel. So this is advanced one, so we don't need to remember. A division node also is represent new processing threads, represent things are running in parallel, but they have slight difference. Let's look at a concrete example. So this is a general ATM scenario. So here, what are the steps? First, get card information, right? So when you input when we want to do transactions on ATM machine, you first insert your card, right? So the ATM machine will get card information. Then you input your PIN information. So ATM will get PIN information. Then you process transaction. You have different types of transaction. For example, you want to withdraw money, you want to deposit cash, you want to check the balance, right? So there you can repeat it many times. So there's an N here. There's a repetition node. Here you see the process transition node is a expanded node because it can be expanded to a further detailed steps. So here we see they actually expanded a subgraph of the process transaction node, right? So here in the subgraph, we see there's a case node. The case node, we see the case node is attached to three other nodes, right? Process deposit, process withdrawal, process balance inquiry. And we see some numbers, 0.001. So these are the probability that the process deposit node will follow get transaction node. That's a probability. And 0.7 is a probability that get transaction will be followed by process withdrawal. Okay. And then after this whole process transaction node, we have a terminate session. Okay. So this is the simple execution graph. Okay. So we see 3 types of nodes, 4 types: basic node, repetition node, expanding nodes, and also case node, right? So I want you to remember these 4 types, okay? So how to analyze the software execution model? So we have a graph here, but actually using this graph, how do we understand the response time of or the CPU usage of an ATM machine, right? So we talk about how to analyze execution graph. So what are purposes of the analysis, right? The first, to make a quick check of the best case response time in order to ensure the architecture and design will lead to satisfactory performance. And we assess the performance impact of different alternatives. We can identify critical parts, which part is very slow. We can derive parameters first for the future models, right? Like system execution model, which is queuing networks. Okay, so what are the procedural algorithms for us to analyze the software execution model? The basic solution algorithms are, first one, we identify basic structure of the execution graph, right? Then we compute the time of a basic structure and reduce the basic structure into computed node. So we reduce a basic structure, a small structure, into a computing node. What is a computing node? We know the response time of this node already, right? And we continue until only one node left. And we repeat this process. And how do we do this reduction, right? So how do we reduce or how do we compute the response time of different structures, like, for example, sequences, loops, or cases? Look at it one by one. So for sequences, how to reduce a graph of sequential nodes, right? So for example, here we have n sequential nodes on the left. So we reduce it to one computing node. Here, the response time of the reduced node is just a sum of the response time of all the sequential nodes, right? And what about loop structures? For loop structures, for example, if here this basic node repeat n times, so we just multiply the response time of basic node by n, right? So what about case nodes, right? So case nodes, so we compute, because there are lots of different possibilities, so we compute the response time for shortest path, longest path, and average path, right? So what is the shortest path? Is the time for the case node is the minimum of the times for conditional executing node. We choose the path with the shortest time, right? For the longest path, it is a path with the longest time. For the average path, it is the time is multiplying each node's time by its execution probability. For example, here, for this case node, so what is the average path? What is average response time, right? So the average response time is T0, which is for the case node, plus the probability of T1 times T1 plus probability of T2 times T2, right? So this is how we reduce a case node. Let's do a small exercise, okay? In this exercise, so I want you to identify the best, worst, and average executing time of this ATM scenario, okay? So here's the two figures. So the figure 4-3, it is the ATM scenario, the whole ATM scenario. And the figure 4-4 is a subgraph, or it's a sub node, which indicates the performance scenario of the process transaction node, right? So I want to, and also the node times is shown in the table on the left. So I want you to calculate the best, worst, and average execute time of this, of the entire scenario of the ATM. Okay, I'll give you 5 minutes. Please do this exercise, and I will tell you what is the result. Okay. If you have any questions, just raise your question either on Slack or here. Okay. And after you have finished it, so you can post your results either through Slack or on room chat. Okay. 5 minutes. Okay, so we get a few results, and yeah, the right answer for the average path is 540.9. Okay, so how do we do the calculation, right? First we calculate the executing time of the subgraph, which is a process transaction node, right? So what's the result? Like first we have 30, right? We use 30 plus actually I post the result on chat. Okay. Yeah, this is for the average, and for the best worst. The best is when you just instead of adding, so the process transaction for the best case is just 30 plus 50, right? And for the worst case is 30 plus 500, right? So for the average case is 30 plus a weighted combination of a weighted sum of the three possibilities, okay? And we also add get card information time 50, get PIN time 20, and also we need to make sure that for the process transaction case, we need to multiply it by 2, right? Because we have repetition, so this process transaction node is repeated 2 times, right? Then for terminate session is 100, we'll add it. So the final result is 50 plus 20 plus 2 times 185.445 plus 100 equals to 540.9. Okay. So do you have any questions here? Okay. If there's no questions, let's continue. Okay. Okay. So here I give you this time for each node, right? But in fact, actually, we don't have this time all the time. Usually, we need to derive the time for each node, right? How can we derive the time for each node? Let's see how do we do the analysis, right? First of all, we start with um, a very simple case, right? And we don't consider many uh, com complex scenarios. We first do a simple case, then we gradually add more information to make it more complicated, more sophisticated. Okay, so it's what is the simple scenario here? Let's look at one example. Um, we look at the so a very simple subgraph, right? So this subgraph called the authorized transaction, right? For the authorized transaction subgraph or the sub scenario, so we have three basic node. The first one, validate user. Second, validate transaction. Then it's a send result node. Okay. Um, so the first step, we need to identify the software resource requirements. So in order to get a time of these parts, we need to identify, so what are the basic software resources that are used in each of these steps. So basically for each basic node, we have to specify the software resource requirements for each service unit. The service unit can be so one DB access, one database access. So one message on the sending one message on the network, or the CPU just process one work unit, for example, one instruction, right? So these are the basic service unit. Like for example, for validated user, it may have the one work units that use CPU, for example, use CPU, one work units, 2 dB or 2 dB units, and zero messages, right? So these are these basic service units that are included in the validated user step. Okay, for validated transaction step, we have two work units, 3 dB units, zero messages. Okay, for send results, two work units, 1 dB, one message, because when you send the results, there's a network involved, there's one message. So we call this one as a software resource requirement matrix. Okay. So this is the first step. So here we map this each step or each basic node to the software resource requirements. But at the end, when we calculate the time, we need to map it again to hardware resources, right? For example, we need to map them to CPU, disk, network, memory. We need to map them to those hardware in order to calculate the time, right? So how do we do the mapping? So we have something called processing overhead matrix, which actually identifies the the processing time or processing the hardware resources used by each unit, software unit. Okay, let's look at just an example here. So first we identify what are the resources, what are hardware devices used in the system. So here we have one CPU, we have one disk, and one network unit, right? And what are the quantity? We have one for each of them. And what are the surface unit, right? The CPU, the surface unit is, so we have a unit of thousands of instructions. For disk is a number of physical IOs. For network is the number of messages, right? And then we map this software resource units to the hardware devices, right? So then here for example, here, the work unit for this unit, software resource requirement unit. So it is mapped to 20K instructions for the CPU and 0 on disk and 0 on network. For DB, it is mapped 500K instructions of CPU to disk IO and 0 network message, right? For the messages software unit, right? We map it to 10K instructions of CPU, 2 disk IO, and 1 network message, right? So we do this mapping. And also for each unit of this hardware resource, we have the time, which is called service time. For example, do 1K instructions on the CPU, it will cost this time, right? It is a 0.01 millisecond. And do one physical IO on disk, the time is a 0.02, and sending one message on the network, the time is 0.01. So we do this mapping. So this mapping is from software resource requirements to hardware resources, right? And for each unit of computation of the hardware, we know the time, right? So we can map the software resource requirements to the time needed, right? So finally, we can calculate the time, right? Okay, so we talk about this. These are the theories, right? How can we do the mapping? Then actually giving actual results, giving actual example. So how we do this, how we calculate the response time for each step, for each basic node, right? For example, for send a result, how to calculate this. The step one is first we use this process and overhead matrix. So we talked about in the previous page to calculate the total computer resources required per software resource for each node in a graph, right? For each node in a graph, for example, for the send result node in a graph. So we use this process and overhead matrix to calculate the total computer resources required per software resource. For example, here send result, we know there are 3 software requirements, right? 2 work units, 1 DB, 1 message, right? And so we know, so for each, from previous page, we know for each work unit, it is mapped to 20K instruction on the CPU, right? And for each DB, it is mapped to 500K instruction on CPU. And for each message, it's mapped to 10K instructions of the CPU, right? So after we get this information, so we can calculate that in total for send result step, we need to use how many CPU instructions, how many physical IOs, how many network messages. For example, here, the CPU requirements is 550. Why is 550? Because it is 20 times 2, right? Because we have 2 work units. And for each work unit, there are 20K instructions of CPU. So 20 times 2 plus 500 times 1 plus 10 times 1. So it is 550, right? For CPU, 550K instructions of CPU. Similarly, So send result node would use 4 physical IOs and 1 network message. Okay, so we calculate for each basic node send result, for example, the total required hardware resources. Okay, and then let's look at here. This is another example, right? This shows more clear how we do the calculation. So here we show the basic step of validate user. Okay. So what is the software requirements? Software resource requirements: 1 work unit, 2 DBs, 0 message, right? And we know the for each software resource unit. So what is the corresponding hardware requirements? So we know here for each work unit is a 20K instruction of CPU and a 0 physic IO, a 0 message, right? So we do this multiplication. So we result in total for validated user. The number of CPU instructions is 1020K instructions. For physical IO, it is 4. For messages, is 0. So and then for each instruction, for each IO, for each message, we know the service time, right? Then we multiply them together, right? Like 1020 times the service time of 1K instruction of CPU, and 4 times, so 1 physical IO service time is 0.02, right? So we multiply them together. So this is the executing time of the validated user step. Okay. So after we get this for one step, right? For each step, then we compute the total computer resource requirements for the whole graph. For example, after we get the results for all the 3 steps, validate user, validate transaction, and send a result, we get, so we get a total hardware resource requirements for the graph, right? Basically, it's a sum of all the 3 steps. For example, here we add the results for CPU, physical IO, and network messages. So the 3 steps would use 3,110K instructions of CPU, 14 physical IO, and 1 network message. Finally, right, we compute the executing time. This executing time is a best case time because we don't consider lots of extra details, right? We just consider it a simple way. So we have this total number of hardware resource usages. Then for each of them, we know the basic service time for each unit. So we just add them together and we get a result of 0.32. So 0.32 is the executing time of the entire graph. So do we have any questions here? If any part is not clear, I can explain. Okay. Okay. If there's no question, let's do another exercise. Okay. And also we will have a break. So this exercise is it's similar to what we have done in the example, right? So I want you to estimate the best, worst, and average executing time of the process transaction scenario. So here we show the process transaction, we show the execution graph of a process transaction scenario. You don't need to look at UML. The UML is just for you to better understand the execution graph. Okay, the UML is a sequence diagram. So you'll probably have learned in your software design course. Okay, and so here we give detailed. We tell you for each step. So what is the software resource requirements, and also in this process overhead matrix, I tell you for each software requirement unit. So what is the corresponding hardware resource used, and also for each hardware resource unit, what is the service time, right? So I want you to calculate the best versus average executing time of this subgraph for process transaction. Okay, you can just look at this slide and do the exercise. I also have a break. So for a break for 5 to 10 minutes. So in total, so let's meet at I'll give you 15 minutes on this exercise, and we have a 5 minutes break. Then after 20 minutes, so which is 2:05, right? I'll see you at 2:05. Okay.